Okay, let's find our stuff. Find stuff. Okay, let's try this. Let's use our first derivative test. And let's find all the stuff that we can with the first derivative test. So we're going to find relative extrema. We're going to be able to identify intervals where the function is increasing or decreasing. Okay? So what do we do?
Find the derivative.
Find the derivative. So what is our derivative?
3x squared.
Okay, 3x squared. Good. Okay, so is that undefined? We got to find critical numbers, right? We're going to populate our table with all of the critical numbers.
Right.
So quick review, it's been a weekend. So where do critical numbers, somebody raise your hand and tell me where's one place where critical numbers exist?
Where the derivative equals 0.
Where the derivative equals 0. Where else?
Where the derivative is undefined.
Where it's undefined. Good. And what's the point of finding critical numbers anyway? Why are we doing this? So. Okay, so they're the possible places where what could exist? Peaks and valleys. Okay, so relative extrema, right?
Yeah.
Okay, so we got to find those. Is this function undefined anywhere?
No.
It's not. It's not. Okay, but we have critical numbers where it equals 0, so we'll solve that equation. 3x squared equals 0 when what? When x equals 0, right?
Yes.
So we get one critical number at x equals 0. Okay, so let's make our table and figure out what's going on here. So there's 0. Tell me, what else should I write in my table? Okay, I can do that. Now, I might even want to put some other stuff in that column.
Oh, 0 down to f prime.
Okay, that's important, isn't it? Because if I have a 0 there, that's telling me that's reminding me that this is a critical number, right?
Wait, why is it reminding me that?
Because we know that critical numbers exist where the derivative has a value of 0 or undefined, right? So that's kind of important. That's telling us this is a critical number. While we're at it, we might as well finish the ordered pair because it's pretty easy to do. We get 5, don't we? We plug back into our function. So the point 0.5 may or may not be a critical, or may or may not be an extremum. It is a critical number exists there though at x equals 0. So now what? Okay, good. We're going to pick some test points around it. So how about if we pick -1 and +1? And what are we going to do?
Plug it in for the derivative.
Okay, we're going to look at the value of the derivative at those places, right?
What do you look
Or not the value, just the sign. Okay, good. Yeah, it is. Look at this. So the derivative here is 3x squared. What can you tell me about the sign of 3x squared, the function 3x squared?
Positive.
Well, it's always non-negative. It could be 0, right? It's 0 is not positive, is neither positive nor negative. So, do you understand the difference? Say it again. Well, if it's 0, in this case, I was just being picky. In this case, it's not. We know that it's the only place that it's 0 is at 0. And so on this interval right here, I was just kind of just math joke, I guess. So over here, so we know that it's positive, isn't it?
Yeah.
For that test point, we know that it's positive, right? If for all values, in fact, other than 0, it's positive, right? So it's going to be positive there as well. So is that a maximum or minimum?
No.
It's not. What is it?
Nothing.
Well, it's something. Because it really does have,
Oh, I know.
what is it? What do you think?
Explain to you it's very common.
Yeah, okay, we know what the shape of this would have to be, don't we? We know this is what we call an inflection point. Okay, it's an inflection point because it's a place, well, we'll talk about why maybe today, if not today, tomorrow. We'll see how far we get. But we know that the look has to be this. We know that it's going to be increasing on this side and increasing on this side, and it has to have a horizontal tangent line. So there's only one shape it could take. The shape is going to be like that, isn't it?
So like a little. Yeah.
Okay. Does that make sense? Because we can see here that there's our horizontal tangent line, right? It does have a horizontal tangent. The slope is 0. Okay? So it failed. That one failed the first derivative test. I don't even say it failed, but I guess we would say it failed because it's not an extremum. It's something important, but it's not an extremum. Okay? Questions on that?
So then what would you do if this was a question? How would you answer it? NA?
I mean, I have to know the context of the question. One of those comes up though, doesn't it?
Yeah, that's how I went over it.
Mm-hmm. It does come up, and I think it just doesn't have, yeah, it's NA, I think, isn't it? If one doesn't exist, you put NA in that question. Yeah, and it tells you that in the instructions. Okay, let's do one more. There's another kind of thing that you're gonna have some questions about. Let's do one like
Is this for
3-3. Yeah, we're still on 3-3. So here's another one. Let's do one like this. How about oh, one other thing I forgot to do on that. So somebody just tell me, well, I'll write it down. You tell me what to write. What are the intervals on which the function is decreasing? Nowhere. Nowhere. Okay, on what interval is the function increasing?
Negative
To infinity. Okay, it's an interesting question though, isn't it? Because is it increasing here or not?
No.
Okay, there would be a mathematical debate here, but I firmly believe that it is increasing. It is increasing because the points around it behave as though it's increasing. In other words, if you had a marble and it was a frictionless surface, you could not set the marble there and prevent it from rolling down the hill. Right? Agreed?
But you can't make it go up a hill either.
No, you can never make it go up a hill, but it's only going to roll down a hill if there's a slope there, right? Does that make sense?
Yeah. Wait.
Because, and here's my argument for this. My argument for this is that if you take this point right here and you compare it to the point next to it on either side, well, there isn't a next to point. But if you take a limit and you look at the value of the point next to it, it is going to be a bigger value on the left and a smaller value on the right and a smaller value on the left, right?
Right.
And so, to me, you can't have a single point that's not increasing on a smooth function. You know what I mean? It's either, it does have a horizontal tangent line, but for how long is the function horizontal? 1 point. That's it. See what I'm saying? And so there would be some debate there. There would be, and different textbooks are gonna tell you the answers are different things. Some textbooks are gonna say that it's increasing on the interval from negative infinity up to but not including 0, and on the interval where x is greater than 0, right? Some textbooks will say that. Some textbooks will say it's increasing everywhere. I come down on the side of it's everywhere. Not that it's a big deal. It's not an important question, really. The calculus part isn't really in progress yet, but that's what I will say. Yeah. Okay, so let's look at one other one here. Let's look at.
Wait, so where would it be increasing then?
So it'd be increasing everywhere.
Oh, so your answer is everywhere?
Everywhere, and with the arguable exception of x equals 0, but you know that's a debatable
In
point.
math way, is it gonna say negative infinity?
With brackets or parentheses?
So no, it can never be. So the interval would look like this, right? Because you can't have a closed bracket around infinity because it's not a number.
Oh.
Right? Okay, so what about this guy? Okay, this is a good one for us to look at because there's some stuff that needs to happen here that we haven't really talked about yet. Okay, so first of all, what I would say is before you go any further with this, we have to identify the domain. The domain has typically been for us all real numbers for all the functions we've dealt with, but this one it's not. Are there any values of x that need to be excluded from the domain? 0. And the easiest way to say that is not x is less than 0 or x is greater than 0. What's the most efficient way to say that?
X doesn't equal
Yeah.
0.
Right, so our domain is just this. X cannot equal 0, right? Okay? That's important. That has an immediate impact on the table that we're going to draw. In fact, before you even go any further with this, I would say that you could, when you're writing out your table here, you could put a value of 0 there, and your function is undefined, okay? Something else that might even be helpful to do would be to put a dashed line through there and just write VA for vertical asymptote, because it is a vertical asymptote, isn't it? 0 is a 0 of the denominator, but 0 is not a 0 of the numerator, correct? And if we ever have that, right, if we have a value of x when we try to directly evaluate and we get a number divided by 0, remember from earlier in the year, that's a vertical asymptote. What's a whole?
And they're both equal to.
Okay, if a number is a simultaneous 0 of the numerator and the denominator, that's a whole, not an asymptote, okay? But this is an asymptote. So what this does is this breaks our function up into two completely separate universes that are separated. We have to treat them individually. That's the important thing I want you to get used to. Okay, so now what? Now what do we do? Yeah, now we differentiate. Okay, so we're going to differentiate here. Let's just go ahead and use the quotient rule. So what are we going to get using the quotient rule?
X squared times 3x to the third.
How many x to the third?
4x to the third.
4x cubed minus the quantity x to the 4 plus 1. We agree top times derivative of the bottom, right? Okay, all over
2x squared.
x squared squared, which is x to the 4th. Okay, so now we've got a little bit of work to do. So we have to analyze, we have to find critical numbers, don't we? We certainly need to simplify this thing. Let's go ahead and do that. What if I were to, you know what, I don't want to yet. Well, yeah, I will. We'll come back and, yeah, we will. So let's distribute the 2x and let's distribute the x squared. And what happens? We just get 4x to the 5th
You just get 1 on top. I mean 2x on top.
minus
Negative
2. I get, well, minus 2x to the 5th. Did I do something wrong there? I don't think so.
No.
2. No, you didn't say.
Minus 2x to the 5th minus 2x. Because I'm distributing the negative 2x all the way through. Okay. Over x to the 4th. And so finally, I guess I can combine like terms, right? And get 2x to the 5th minus 2x over x to the 4th. Okay, good. Okay, now what? Yeah, so now we got to find critical numbers. Okay, so here's kind of another issue that comes up. And I think some people have asked questions about this and might already have a little insight into the answer here, but where we look for critical numbers where the derivative is undefined or equal to 0. So is the derivative equal to 0 anywhere?
Yeah.
Yeah, where?
Where the numerator says 0.
I mean, did I say 0? Did I say undefined, right? So I said 0. Let's do the other one first. Sorry, I was thinking ahead.
Yes.
So is there any place where the derivative function is undefined?
Yeah.
Where's that going to be?
0.
No.
At x equals 0, it's undefined. Is that a critical number?
No. Wait, isn't it a whole of function? Well, you're
Okay. Go ahead, ask that question.
Isn't it a whole of function?
Oh, okay, you're right. Okay, but it's still undefined. Even a whole is undefined, right? Okay, but my question is, let me say this again. I'll go slowly with this. My question to you is there any place where our derivative function is undefined? And you correctly said, yes, there is at x equals 0. Now my next question is, just think about this for a second. Is that a critical number?
Yeah.
I mean, it seems like it ought to be, right?
No.
But it's not for what, tell me why maybe we wouldn't consider that to be a critical number.
No, because it's like a vertical asymptote.
Yeah, because,
It's not a extreme.
right, it's not in the domain of the function. And there's kind of an unspoken, agreement when we're looking for critical numbers that we're really only looking for critical numbers where they would be of any use, which is in the domain of the function. What good is a critical number at a place where the function doesn't even exist, right?
Anywhere it's not.
None. Critical numbers are just there for us to locate the places where we need to look for extrema. So we only need to look for extrema within the domain of the function. And so once again, we see that when we get this exclusion, right, we're going to restrict our domain in this way, then any critical numbers that fall inside that restriction we can forget them. We don't have to deal with them, which I guess is kind of good. It makes things a little easier, right? So there's no place in our domain where our first derivative is undefined. Okay, now we have to ask the question, let me make a note of that. So no undefined critical numbers, right, in the domain. Now, are there any places where our first derivative equals 0?
Yeah.
Yes. Now, where can we trade our big ugly function for an easier equation that's going to identify the zeros of the derivative? In other words, the derivative of a ratio, excuse me, no, the 0 of a ratio is the same as the 0 of the 0 of a fraction, 0 of the numerator. I said that in kind of a weird way. Let me restate that. So we know that if I have a rational function, I have a function that's got that pieces on the top and the bottom, I know that the function as a whole will equal 0 when its numerator equals 0. The function will be undefined when its denominator equals 0, right? Does that make sense?
Yeah.
So we can trade this, and we can just make the statement then, f prime equals 0 when the denominator or numerator equals 0. 2x to the 5th minus 2x equals 0. That's much easier to solve. Okay, so what do we get? How do we deal with that equation? Okay, we could divide both sides by 2, factor out an x, leaving us with x to the 4th minus 1. And so what are our solutions? 0, which we don't care about, but the other ones we do are, and negative 1, right? Because now let's talk about why that is. I'm going to solve the equation. If I set this factor equal to 0 and solve, we get x to the 4th equals 1. If I take an even root, not just a square root, any even root of both sides of an equation, I always have to introduce plus or minus. Good. So x is plus or minus 1. So those are our critical numbers where the first derivative is 0. Okay? So now, what? We could do that. We could plug them back in to get the values of the function if we want to. That's kind of optional. Sometimes we'll need to, sometimes we won't. Usually, probably we do. We'll skip it for now, because that's not really what I'm after today. But we could. But we want to know if those are maxima or minima or neither, though, right? So what are we going to do to find out? What does that mean? What are we going to do? Test points. Yeah, okay, and where are our test points going to be? Okay, so could 0 be a test point? No. In fact, remember that this vertical asymptote is like a wall, right? It divides the function up. So you tell me good locations of test points then. Okay, 1/2 would be a good one because 1/2 is between the asymptote and the next critical number to the right. Agreed? Okay, so 1/2 would be good.
1 and 1/2, 2.
1 and 1/2, or how about picking like 2? Pick an integer, make it a little easier. On this side,
Don't you not, why would you need to do the other side?
because we have to know what's going on here.
But isn't it just gonna be like linear?
You know what? I hadn't planned on talking about that today, but when we're all done, maybe you could tell me why it would be a mirror, if you know. Because it doesn't always have to be, but in this case it is. I like the way you're thinking though, that's good. We want to use symmetry, but we'll talk about why here at the end. So we're just going to find the sign of the derivative, right? Now, do we want to use, when we're doing the sign of the derivative, wouldn't it be easier to treat the derivative as being factored? I'll tell you why. Because I could just use the derivative in this form, right? But that's a little bit hard to judge if something's positive or negative when I've got a sum of terms on the top, right? And then just a factor on the bottom. But what if I just quickly factored that? Because I essentially did anyway, right? So let's replace that with 2x times x to the fourth minus 1 over x to the fourth.
What did you just do?
erase it?
So I just factored out a 2x. Okay. Here's why in general it's good to have this factored, because now when I want to find the value of the first derivative, look what I can do. I'm going to take the value at, let's say, -2. Well, f prime of -2 just equals the sign product of the signs of those three factors, which are relatively easy to find. So when x is -2, what's going to be the sign of the first factor? Negative. So here's how I do this. And this is just my way. I mean, this is not like you'll probably see this in a textbook. But I just do that. So I know I've got a negative factor times when x is -2, what's that going to be? Positive, right? Because I'm going to get a big positive number minus 1. Okay? Divided by positive, because it's an even power, right? And what's that sign going to be? A negative times a positive divided by a positive. Negative. How'd you know so quick? How, if I had a whole string of factors there, how could you really quickly know what the sign's going to be? Say it again? Because if there's an odd number of negative factors, then it's negative. If there's an even number of negative factors, and 0 is an even number, then it's positive, right? Yeah. So we get negative here. What about at -1/2? How is that going to change for -1/2? That's going to be the same, that's going to be the same, but what's going to happen there? It's going to be negative, isn't it? Because I'm going to get 1/2, or -1/2 to the 1/4, or to the 4th power, sorry, is going to be a big, or a very small positive fraction. I guess I'm getting everything screwed up here. Right, I'm going to get 1/16.
Yeah.
Right, 1/16, and I don't even care what it is, I just know it's going to be less than 1. Minus 1 is negative, right? So that's going to make that one negative, and then I get negative times negative, so I'll write it down. F prime of -1/2 equals negative over positive, which is an overall sign of positive, okay? How about over here? At 1/2, I'm going to get positive, negative, positive. Everybody agree? Equals negative. Yep. Okay. And what about at 2? Everything's positive, right? So then what's this going to look like? If what is this? That's a valley, isn't it? Okay, because I'm going from decreasing to increasing smoothly, and this is valley. Right? Rounded valley. Okay? And this is an asymptote, and so this is jumping the gun just a little bit, but in section 3.6, the goal is just to be able to put all this stuff together. It's supposed to be a prime, isn't it? Put all this stuff together and sketch the curve. Well, we can do that here, right? We can sketch this pretty easily. We know that we had an asymptote at 0, and then I had 2 valleys, and if we did go back and just fill in the value of the function, what do we get? If I plug in -1 or +1, I'm just going to get 2, right? If I evaluate this function at -1 or +1, I get 2 over 1. So my function is just going to look like this. Those are my extrema, and they were both minima, right? So then the function is just going to do, it has to stick to that asymptote, right? So it's going to come down and just go like that, right? See what I'm saying? Okay? So we do get a sketch of it, okay? All right, so next thing I want to show you then. That you can, what's that? How many minutes?
4.
Oh,
Will you go back?
Washington trivia.
Yeah, you go back first.
Will you go back?
Yeah. You want me to go down?
3 minutes.
So Hunter's here.